Here in Chapter 10, we're going to be talking about roots, and I'm sure this is something that you've seen before in a previous class, but in the previous class, you may only have seen square roots, and you might not be aware that they're part of a bigger structure. The symbol that you're used to actually can have a number inside the little dent of the square root symbol, and if there's a number in there, it's important to realize that controls what exponent you're trying to get over there. So when you're talking square roots, you're trying to get something squared that comes out equal to the number you're looking at, like square root of 49. You expect that to be 7 because 7 squared is 49. But if you put a number inside the little dent part of the root symbol, you might be trying to get something cubed or fourth power or fifth power to equal whatever number's inside the symbol. So this is an important weird case in mathematics where if there's a missing number, where you don't see a number, this is the only place where a missing number means 2. Usually a missing number means 1, like 5 over 1, you usually just write 5. So the missing denominator there would be 1. Usually if you don't write something, it's 1. Here, if you don't write something, it's 2. There's another important distinction, though, that may not be at all obvious, and that is that when you just have a symbol like this, square root of 49, versus the definition of what we think that means, something squared equals 49, that's like looking at the difference between an expression and an equation. An expression can be simplified, but it's meant to stand for just a single object. It doesn't have an answer, really. It is an answer. Whereas an equation is solvable, and the important thing about an equation is that an equation can have more than one answer. You know, something squared equals 49. Well, what about negative 7? Negative 7 works just as well as positive 7. And this leads us to a bit of a tricky thing, because we want expressions to be just sort of singular things that just exist, and they don't have choices and maybes about them. So that square root symbol that we're using over here, the actual definition of that is not quite what we had up here. When we said that the nth root of a equals b means a equals b to the n, that's not really 100% correct. There's an extra little bit that has to be added to that. So the actual definition of what that symbol means has this extra word, principal, square root of x. It's actually the principal square root of x. And the word principal, what that means in this circumstance is it means if you have a choice, take the positive one. And the reason why I say if you have a choice is in some cases you don't have a choice. Like if I asked you to do square root of 0. Square root of 0, there's only 0. There's no negative 0 to consider as a possibility. But most of the time you have a choice between a positive answer and a negative answer. The principal root, we want to take the positive square root, not the negative square root. Now that seems like a fairly basic idea. It basically says don't go weird on me, stay positive whenever possible. But it has a strange little side effect. There's a funny little side effect of this idea. And the side effect is that although instinctively it feels like a square root is the exact reverse of squaring something, so they ought to cancel each other out. The square root of x squared ought to just cancel out to x. It doesn't actually quite work that way. It doesn't really actually cancel out like you think it does. So as much as you think that's true, and it's true sometimes, it's not always true. Let me show you what I mean. We're going to try some numbers for x. We're going to actually put an x in there, and we're going to square it and then take the square root and see if we're back to x again. So, for example, if you start with like 5. 5 squared, and then take the square root. Well, 5 squared is 25. Principal square root, remember it's the square root symbol, means principal square root, comes out to be 5. So when x was 5, the square root of x squared came out to be the same as x. Well, let's try it with something else. Let's try 11. X equals 11. So now we're going to do square root of 11 squared. That's square root of 121, which principal square root is 11. So you're probably looking at this thinking, well, Mr. Adams, you just said it doesn't always work. It looks like it always works. Hold on a second. Let's try -3, say. So we're going to do the square root of -3 squared. -3 squared is 9. And the principal square root of 9, remember, that's what this symbol means. The principal square root of 9 is 3. So we started with -3. That's not x. So basically, the issue is, if x is a positive number, then the square root of x squared is indeed equal to x. But notice what happened here. If x is a negative number, the square root of x squared converts it to positive. Now, if you think about that in words, you've heard that before. Positive numbers come back again without changing. Negative numbers get converted to positive. I know you've heard that before because that's the absolute value. In other words, the square root of x squared is the absolute value of x. This is the equation for the absolute value of x. You probably weren't aware that it had an equation. Now, honestly, although that's kind of cool that the square root of x squared is the same as the absolute value of x, it's nice that we've got an equation for the absolute value of x now. It's also kind of a pain because remember, this is replacing a cancellation principle that we wanted to be able to work with. We wanted to be able to say square root of x squared canceled out and gave x. And instead we're getting square root of x squared is actually absolute value of x. And that's annoying. So what you're going to see in a lot of the homework problems is they're going to say something like this. They're going to say, assume all variables represent positive quantities, or assume no quantities were created by raising negatives to positive exponents, or something like that. They'll say something that basically says, don't worry about negative numbers, and if you don't worry about negative numbers, then you get to do the cancellation exactly the way you'd like. Then you get to say that the square root of x squared is equal to x. But only if you're not thinking about negative numbers. Only if positive numbers are your universe can you say that. Okay, so all of this has been talking about square roots, which you thought were familiar and you've seen a long time ago. We also need to talk about the other types of roots. Because remember, there can be a number in there that's not 2. So if you put a number that's slightly more complicated, like for example 3, we get a type of thing called a cube root. And what you're trying to do here, remember, is get an exponent of 3 that produces 8 or 27 or 1,000 or whatever as an answer. So here what you have to do is think in your mind of some number that when you cube that number, you get an answer of 8. And I'm pretty sure you've already thought of the number because it's a pretty small number. It's the number 2. 2 times 2 times 2. 2 cubed gives you an answer of 8. So that means the cube root of 8 is 2. It's the reverse of cubing. It's uncubing, you could say. It's the exact opposite of cubing. Same idea over here. You're trying to imagine some number that when you cube it, you get 27 as the answer. And it's really honestly just guess and check. You try 2 and that's too small. You try 3 and it works. And since 3 works, the answer is 3. I bet you've already jumped ahead and worked this next one over here. Some number cubed gives you 1,000. Yeah, sure enough. So if you're trying to justify this, if you've got the answer already and your friend doesn't understand why that's the answer, say, well, 10 to the third, it's 1,000. So the cube root of 1,000 is 10. It's just the reverse of cubing. And there's one really key example you have to understand if you want to understand not just cube roots, but sort of the big picture of roots overall, and that is the cube root of -8. And the reason this is an important one is back when you were learning square roots, you learned square roots of negatives don't exist or something like that. Well, cube roots are a different story. Think about it. If I do -2 times -2 times -2, in other words, if I do -2 cubed, what do I get? What's 3 negatives multiplied together? Doesn't that come out negative? And 2 times 2 times 2, doesn't that come out to be 8? So if -2 to the third gives you an answer of -8, then the cube root of -8 is -2. So unlike square roots, which have this very sort of love-hate relationship, well, it's more like a hate-hate relationship with negatives. They just don't work well with negatives at all. Cube roots work with negatives just fine. Absolutely no problem at all. Just work like positive numbers. And this also means that weird side effect with the absolute value we were just looking at is not going to happen here. If you take the cube root of x cubed, the answer is going to be x no matter what. Even for negative numbers, it'll work just fine. So for square roots, you got to worry about absolute values when you try to do cancellation. For cube roots, you don't have to worry about it. And if you're thinking ahead a little bit, what if the exponent's larger? What if it's a fourth power or a fifth power or sixth or seventh or eighth or ninth or 10th? It turns out that it's an even versus odd thing. Even roots with even exponents, that's where you get absolute values. But odd roots with odd exponents, you don't. So that's sort of the overall big picture for that absolute value versus non-absolute value thing. And of course, if we just say, let's stick to positive numbers only, it's not even a problem at all. One last topic, since we're talking about cancellation, we need to talk about cancellation when the exponents don't match exactly. When they do match exactly, you can imagine what the answer is going to be. And for all of these, let's assume no negatives. Let's just put that as a ground rule for these examples here, so we don't have to worry about absolute values. And with this example here, since those exponents match exactly, you should know that that's going to be x for sure. But something like this one or any of these other 4 that we've got here, the exponent and the root aren't matching exactly. Like this one on the far left, we're trying to think of something squared that gives x to the 8th as an answer. And the thing squared that'll give you x to the 8th is x to the 4th. X to the 4th squared gives you x to the 8th. So the square root of x to the 8th is x to the 4th. Same idea here for this next one. Something squared has to give you x to the 10th. And really it's sort of guess and check, but kind of easy guessing and checking. You'll probably guess right the first time. You get x to the 5th. This next one's a little bit tricky. We want to get something cubed coming out x to the 6th. Yep, sure enough, x squared cubed gives you x to the 6th. And then this one down here, we want something to the 4th, giving you x to the 8th. And yeah, that's x squared there also. And if you look at all of these, if you look at every example I've done here, I bet you're already inventing a shortcut. I bet you're making a shortcut up just sort of naturally using your normal human instinct. So try using your shortcut on these 4 here and pause the video and then press play and see if you get the same answer I get. All right, here are the answers you should be getting. This one comes out x to the 5th. So does this one. This one here is x to the 25th. And this one here is x to the 9th. And if you got all of those answers, I bet you've already figured out the rule that says if you have a situation like this, some number here and some number there, the way the root and the exponent cancel is by taking the exponent and dividing by the root. Keep this in mind for next time when we go on to section 10.2.